Okay, in the last video, we went over what the basic transformations of any parent graph are. In this video, we are going to drill down about the effect of transformations on a sine and cosine graph in particular. Now, all the graphs that you will see are sine waves, but you need to understand that cosine waves have the same period. They're just slightly different than a sine graph. So we're showing you a sine graph, but all of these rules apply equally to a cosine graph as well. All right, so let's take a look at our structure. We've got A times the sine of B times X minus H plus K. And like we discussed before, you know that all of these except for B you have learned before. And we learned that B is a compression or stretch horizontally. A is a compression or stretch vertically. Okay? And it's very important to note that the y value of the peak of the wave is the amplitude itself. So, if you're looking at a function that says 2 sine of x, it's going to look like the blue line. Note that the zeros are in exactly the same place as the zeros are in exactly the same place as the original points. And the only difference is that the peak and the valley of the wavelength equals whatever the amplitude is. So this is -2. See, -2. This is +2. Note +2. Okay, moving on. So now let's go to B. So B equals the period or the wavelength of the function, and the symbol for that is lambda. And I just want to make it clear that although many math teachers use the word period to describe this stationary length of a sine wave or a cosine wave or a tangent or a cotangent wave, the actuality is, this is important, the word period should only be used in sciences such as physics, where the waves are in motion. Here, we're looking at a stationary graph. Nothing is moving. So technically, you should use the word wavelength. Although, like I said, many math teachers use the word period. Anyway, the fact is that this length, this amount, is the amount of the graph that is unique before it begins to repeat. Lambda for sine and cosine is 2 pi. Lambda for cotangent and tangent is pi. And the way you figure that out, whatever the period is going to be, or the wavelength, it is going to be 2 pi in the case of sine and cosine. So it's whatever the period of the parent function is divided by the absolute value of B. Okay, this is B. The 2 is B. So for the case of what we're looking at, we've got a graph here, our standard sine of x. There are 5 points. And then what happens when I multiply that by 2 is I compress the graph horizontally, and I find out that the entire period is now pi. That means when I divide that into 4, I've got the start, pi over 4. Pi halves is now my center. 3 pi over 4 is negative 1. And then I go back to pi, where my cycle ends. Then we have horizontal shift. That's H. The horizontal shift is literally a shift horizontally in the direction and distance of the starting place of the graph. So what does that mean? Well, let's look at this black, the parent function, sine of x. You can see it starts at 0, 0. It goes to the 5 points that you learned from Robert Adute. 0, 0, pi over 2, 1, pi 0, 3 pi over 2, comma negative 1, and 2 pi 0. So the way that you find out what the period is, what the horizontal shift is you set this entire piece to 0. This piece of a function is called the argument. It is the x-coordinate, as it will, because you can't just deal with x. You've got this minus pi over 4. So all of this needs to be taken as one entity. It's called the argument. It's the independent variable of a function. So when you set the argument to 0, this will tell you where you start. And then to graph, you plot your major points and draw a curve. For sine and cosine, it's whatever the period is divided by 4. So in the case of this graph that is shifted, but nothing else is happening to it, then what I will do is I will take the period 2 pi, I will divide it by 4, and I will get pi halves. That means that wherever my starting place is, which in this case is pi over 4, I've shifted this graph to the right, pi over 4. You see this? Here's the shifted graph. So now to get my points, I'm going to add pi halves to every spot. So I'm starting with pi fourths. If I add 2 pi fourths, which is pi halves, I get 3 pi fourths. That's my high spot. Okay, so let's add another 2 pi fourths. I end up with 5 pi fourths as a 0. And then let's add another 2 pi fourths. Wow, that gives me 7 pi fourths. That's where my lower level is. And then we have to leave the graph behind to get back to 0. Okay, and that would be 2 pi plus pi fourths. So that would be 9 pi fourths. Last but not least, I know this is a little long, we'll live through it. Last but not least, we have our old pal K. And K is a vertical shift. And in trigonometric terms, it also is a midline shift. Let me explain what I mean by that. So once again, the black line represents our parent sine function. All right? And the orange graph represents the sine of x plus 1. Okay, so K, the number 1, actually equals the midline of the graph. So no matter what K is, that number is the midline of your graph. So much like the amplitude will equal the y value of the height of the peaks and valleys, K equals the midline of the translated graph. So in this particular problem, we have that sine of x plus 1. So we have therefore shifted the midline of this graph from 0 to 1, up 1. And then we can draw as we normally do. Okay, on Thursday, we put it all together and plot different